Valence electrons. So valence electrons are the electrons in the outermost principal energy level. So that's N. N equals 1, 2, 3, 4. Whichever is the highest N that has electrons in it, the electrons on that level are the valence electrons. In the quantum hotel, that would be the highest floor that has anybody staying on it. Regardless of price, if you've got somebody staying on the 4th floor, even though the 3D room isn't full, if you've got somebody on the 4th floor, those are the valence electrons, the guys on the highest floor. So what we see in the main group elements is that the group number corresponds to the number of valence electrons. So this is very convenient. This is the US usage group number, not the IUPAC. So this is the 1A, 2A, 3A through 8A. The noble gases are in group 8A. They have 8 valence electrons. Oxygen's in group 6A. It's got 6 valence electrons. Very convenient. The number of valence electrons has a huge effect. It's one of the most important factors in how an atom behaves. So very important to be able to look at the valence electrons. Okay, so here is part of the periodic table, just the first 3 periods. So here we have hydrogen and lithium and sodium. They are all in group 1A. They all have 1 valence electron. If you look at the electron configuration, I mean, hydrogen only has 1 electron, but lithium has 3 electrons. Here we're just showing the outer electron configuration. The first floor, the 1s room, would be full. We'd have 1s2, and then there'd be 1 electron in the 2s. So it's got 1 electron in the second level. It's got 1 valence electron. Beryllium has 2 valence electrons. Boron has 3, 4, 5, 6, 7, 8. So neon, its full electron configuration is 1s2, 2s2, 2p6. 2 is the highest number, highest principal number, and so we're going to look at all the electrons in that level, the s and the p. So 2 plus 6 is 8. The reason that elements in the periodic table have similar properties, chemical properties, to other elements in the same group is that they have the same number of valence electrons. That's why they have similar properties. Any questions?
So 8 would be what exactly?
Group 8A has 8 valence electrons.
No, you said, oh, okay, gotcha.
Now, what about helium? Does helium have 8 valence electrons? It's an exception. It's one of those little guys. It only has 2. Yeah.
So why would it have 2s1 instead of 1s?
Well, it does have 1s electrons. So that's a good question. Let's look at lithium. So for lithium, it's got 3 electrons, and so its full configuration is 1s2, 2s1. So essentially what we're doing here is sort of the noble gas shorthand way. If we did the noble gas, it would be helium and then 2s1. And so if we looked at sodium, sodium would be neon's electron configuration plus 3s1. Because it's neon with 1 more electron. It gets very crowded to show the whole thing in the little box. Any other questions? If you have a question, somebody else probably has the same question and would be very thankful if you ask. Okay, let's write an electron configuration for phosphorus, and we're going to identify the valence electrons and the core electrons. So this is our early times yet. So let's think about how many electrons. So 15 electrons. I'm going to draw the orbital diagram. That's what I'm going to do. So there's 1s and 2s and 2p and 3s and 3p. Everything's all, kind of nice and predictable up to this point. So let's put our electrons in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we could write the electron configuration from that. It would be 1s2, 2s2, 2p6, 3s2, 3p3. This seems like just a lot of numbers and letters strung together, not meaning anything. That's why I really like the orbital diagram, because this is the picture that we can kind of see what's going on. And then this is the shorthand that describes the picture. Okay, so there's the electron configuration. We're supposed to identify the valence electrons and the core electrons. Valence electrons are in the highest principal level. So the principal level is represented by these big numbers, 1, 2, and 3. So of those numbers, which is the biggest? 3. So these are in the highest principal level, but S and P are both in that, right? So these are the valence electrons. They're on the highest floor of the hotel that has anybody staying on it. Everything else is the core electrons. Okay? So if we're looking at the electron configuration, these are the valence electrons, and these are the core electrons. On a test, this would probably be multiple choice, and I'd probably say, how many valence electrons and core electrons does phosphorus have? And then there'd be choices.
Like, would you be asking how many electrons, basically? So, just count up the electrons. So,
well,
valence.
I don't know. Yes, question.
3s is included in the valence electrons?
Yes.
They're paired up?
Yeah, 3s, the 3s electrons, that's the envelope right there. 3s electrons and the 3p electrons are both considered valence electrons because it's the electrons in the highest level, highest principal level.
No matter if
it doesn't matter if they're paired up or not. It's just how many electrons are there. Yeah.
Why is 2s and 2p considered the core electron? Why is it?
Because they're not valence electrons.
So
core electrons is everything below.
Okay.
So, if you think about like a piece of fruit, maybe an onion. Because ogres are like onions, right? I always think of Shrek. Okay, but think of an onion, maybe one of those, red onions. And there's the red skin on the outside that you don't want to eat. You peel that off. And then there's layers underneath, right? So the valence electrons are like the dry red coating on the outside. And then there might be lots of different layers inside, but those are all in the core, the inside of the onion. Does that make sense? So there's one valence level, and everything below that is core. Any questions? Okay, now we're going to see how this comes from the periodic table. So we can divide the periodic table into 4 blocks that represent the filling of the 4 different quantum sublevels, S, P, D, and F. The group number for main group elements is equal to the number of valence electrons for that element. So that's a really easy shorthand thing because a lot of stuff, we just need the valence electrons. We don't need to actually write the electron configurations. We just need to know how many valence electrons does this have. And it's right up there on the periodic table. The row number corresponds to the highest principal quantum number for that element, for the main group elements. So here is a color-coded version of the periodic table. So over here, these two columns represent the S block elements. And helium, in many ways, should be over here. So let's just put him over there. So helium is over there, and that's 1s2. Okay, so how many electrons fit in an s orbital? 2, right? There's 2 columns. Over here, the pink, that represents the p block. The p sublevel has 3 orbitals and can hold 6 electrons, right? 1, 2, 3, 4, 5, 6. What? Okay. Yellow represents the d block. The d sublevel has how many orbitals? 5. 5 orbitals can hold 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the F block down here. I won't count to 14. 7 orbitals, 14 electrons. There are 14, they're very short columns, but there are 14 columns there. Mendeleev put this periodic table together in the late 1800s. Quantum mechanics comes along with all this fancy math and stuff, predicts things, and we end up with these sublevels matching up with the periodic table that he put together based on patterns. That is amazing. That is like one of the coolest things ever. It's just, wow.
So what about like LV? How would you like LV then?
Where is LV?
LV is 116.
Oh, 116. Why do you want to do that?
Because it's out of the range. So like how would you?
Well, that would end. So LV down here, livermorium or something, I don't know what it is. So it would be radon, the electron configuration for radon, plus 7s2 and 6f14, 5d10, 7p4.
Okay.
You just read it off the periodic table. So let's look at something like, we just did phosphorus, right? So you can read this off the periodic table. I think of it as, you're just counting across, and each block you come to, you're adding an electron. So here's 1, and this is the S group, 1s1, 1s2. And then we're into 2s, 1 and 2. So 2s2. And then we get over here, this is 2p, 1, 2, 3, 4, 5, 6. 2p6, we come over here. 3s2, we jump over here. 3p, 1, 2, 3 for phosphorus. We didn't get into these guys at all. Anybody have any questions yet? So it's actually pretty easy to remember how many electrons fit in an S sublevel. Well, you count the columns, there's 2. And then there's 6, and there's 10 and 14. Yeah.
Is F lower energy than D? So like if it was 6
Okay,
would it
so
go 6F or 6? And then
yeah, so the D's and the F's and the P's, they once you get here, they get all jumbled up. And this is how you remember what they are. So over here, the period number is the principal quantum number for the S and the P sublevels. These guys, the D block, so I'm going to erase hydrogen helium because it's in my way right now. This looks like it's coming downstairs, right? Like there's this nice little pattern here, and wait, what happened? I think of this as having sunk down a level. So that these guys, in some previous existence should have been up here. And so for them, n equals the principal number, it's the row number minus 1. It's the row number minus 1. So for these guys, they're in row 4. They're going to be 3D. And this is 4D and 5D and 6D. So as you come across, you've got 4s1, 4s2. When you get here, this isn't 4 anymore. This is 3 because it's sunken. So this is 3D, 1 through 10. And then P block, again, it's the same as the period number. So this is 4P. And you come across here, 5S, and then these would be 4D because they're sunken. And then these guys aren't sunken, so this is back to 5P. 6S, this would be 5D, and then what's up with this? Well, on our wall, we have the periodic table in its actual form, where you really need to cut it apart here and separate it and stick these guys in there, right? Because this is number 57 and number 58's down here. So these have sunk twice. And so here, for the F, N is the row number minus 2. So the lanthanides here are in period 6 because they come after lanthanum. That's why they're called that. So this isn't 6F. This is 6 minus 2. These are the 4F orbitals filling. And when you get to number 71, then you come back up here to number 72. That's hafnium. And now this is you're filling up the 5D. So there's this weird little glitch here where one of the 5D orbitals fills, and then it goes in and fills up the Fs instead.
So if it was LA, which is 57,
Mm-hmm.
it would just be go to 5D, but then if it was 58,
Right.
The F would jump in front of the 5D.
Well, yeah. Because overall, the 4F orbitals fill before the 5D orbitals. It's just these two, lanthanum and actinium, that are exceptions. And we're going to see there are some exceptions. I'll tell you which ones are important to know and which ones are not. This is not too significant. So if we're going to do chlorine, so we find chlorine on the periodic table. To do the inner or the noble gas configuration, we go up to the previous row and find what is the noble gas that's there. It's neon. And so we can call this neon, put brackets around it. That means, okay, the electron configuration of neon, and now we're just going to add on the stuff that comes after neon. So we come to this row. This is the third row. 3, this is the S block. We're going to fill this one and this one. That's 3s2. And then there's nothing here. We come over here. This is also row 3. This is the P block. 1, 2, 3, 4, 5. 3p5. Any questions? It's going to take a little practice. Once it clicks, you'll go, oh, wow, yeah, you just read it off the chart, basically. You know, it's like playing Battleship or something. It's like, A5. Well, it's, columns and rows, and you just pick the place, right? And you read it off. And so, this one right here is going to end with 6p1. This is going to end with 4d2. This one's going to end with 4, it's hard without the little gap there, with 4f2. So you can just read it off. Any questions? Okay, use a periodic table to determine the electron configuration of bismuth. Now, these will be asked as multiple choice questions on the exam because I don't enjoy reading your scribbles of long electron configurations and making sure that they're all exactly correct. So I'll give you typed choices and you have to pick the correct one. So you won't really have to decide, should I use the noble gas configuration or do I have to do the full one? Because it'll be one or the other. I'm not going to try to trick you on that. On a worksheet, it might specify the full electron configuration or the noble gas configuration, and so there you do need to pay attention to that. Bless you. We're going to do both of them for this. Okay, so we have to find bismuth on the periodic table. And the nice thing about this is you can write electron configurations even if you don't know the name of the element. So there's bismuth. So I can tell just from its position, it's in row 6, and it's in column 5. It's got 5 valence electrons, and it's 1, 2, 3 into the p block. So this is going to end with 6p3. I can tell just by looking at it. To do the noble gas shorthand, we're going to go up here and find the previous noble gas is xenon. So we're going to write xenon, and then we're going to fill in what comes after xenon. So here, there's 6s, and there's 2. And then we've got this 5d1, and then we're going down here. So we've got the 5d1, but we're not going to write 5d1 and then 4f and then go back and add more 5ds. We're going to put all the 5ds together because that's how we do it. So we've got these guys down here. This is 4 and this is 5. So we're going to come across here. Going all the way across, you don't have to count because it's 14. So that's the 4F block. What did I do? I don't want this. That was a mistake. So we've got 4F, 14. And then we're going to come back up here and go all the way across here. That's 5D, 10. And then we're coming in here. This is 6p, and then we count 1, 2, 3 boxes. Okay? It's just counting along on the periodic table. It's really great to understand the concepts behind it, but bottom line, you need to be able to do this. This, being able to understand valence electrons, becomes really important in organic chemistry, which many of you are planning to take. It's a bad E. Well, what if we weren't doing this? Well, then we'd fill in just counting across the periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and then we get over to here. You know, you get the hang of this, so you can see it on the periodic table, and you can amaze your friends. You're like, how did you say all of that? And then you can actually say the whole thing again, just exactly the same, and it sounds like you're speaking some foreign language or something. Write electron configurations for each element. Okay, so we don't have a periodic table here on the screen, but we've got one on the wall. So for chlorine, what's the last term in chlorine's electron configuration? 3p5. Because it's in the third row, and it's over in the p block, and it's 5 squares in. So it ends in 3p5. So 1s2, 2s2, 2p6, just going across the periodic table, 3s2, 3p5. You can check yourself by adding up the superscripts. They should add up to the atomic number for chlorine, which is 17. How about silicon? What does silicon's configuration end with? 3p2. Because it's just 2 into that block. And the part at the beginning is the same. And then we could look at these and say, well, how many valence electrons and how many core electrons? Well, chlorine has 7 valence electrons. And how many core electrons? 2 plus 2 plus 4 is 10. So silicon, I wrote that up a little too high. How many valence electrons does it have? 4. 4 valence electrons. How many core electrons? 10. Okay, strontium. What is strontium's?
5s2.
Ends with 5s2. It's just like, should be jumping out at you on the periodic table. It's in row 5, and it's in the second column. That's the S block. It's in the second position. It's 5s2. So, the whole business ahead of 5s2, I'm sorry, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then, be careful. 4s2, and then we go to the Ds, but those are one lower level. So that's 3d, 10, and 4p6, and 5s2. How many valence electrons does strontium have? 2. 5s2. These are the valence electrons. How many core electrons does it have? Yeah, 36. So this is 2 valence electrons, 36 core electrons. Okay, oxygen. 2p4 is the ending of it. 1s2, 2s2, 2p4. How many valence electrons? 6. How many core electrons? 2. The number of core electrons for the main group elements corresponds to the number of electrons that the previous noble gas has. So if you look at the noble gases, helium has 2, neon has 10, argon has 18, krypton has 36, xenon has 54. Those are the number of core electrons you're going to see for main group elements. Any questions? Yes? The what?
Noble configuration.
Yeah. So for some of them, the noble gas configuration doesn't seem much easier. Like for oxygen, the noble gas immediately before oxygen is helium, right? So we write helium. That is doing this part, and then we have to write the rest of it. For strontium, the noble gas configuration saves us a little bit more, right? Because that's the electron configuration for krypton. Wait a minute. Sorry, I didn't go far enough. For krypton. So, krypton 5s2. That's a lot shorter. Any other questions? There are some irregular electron configurations because, if there's a nice pattern or a rule, there has to be something that messes it up, right? Always happens. Okay, so because of the sublevel splitting, the 4s sublevel is lower in energy than the 3d. And so we do observe that the 4s fills before the 3d. But that difference in energy is not very big. It's pretty small. And so some of the transition metals, those guys are kind of squirrely and unpredictable anyway, they have irregular electron configurations where the ns, the s orbital, only partially fills before the d's start filling, or it doesn't even fill at all. These electron configurations are found experimentally. We can't always predict what they are. So here they are. So chromium, we would expect chromium to have this electron configuration, 4s2, 3d4. But it doesn't. It's 4s1, 3d5. No, okay. I'll draw them. So let's think about what's going on here. Yeah, I can get them in there. So here's 4s and here's 3d. So what we expect, we've got 6 electrons after argon. We expect that the 4s would fill up first, and then these guys would go in there. Right? That's what we've learned. But that's not what happens. What happens is that this guy comes over here. Let's see if I can do that. Isn't that nice and symmetrical? And everybody has their own bed. Just let's spread out a little bit. The reason that this can happen is that there is less repulsion when you've got completely full orbitals, sublevels, or half-filled. So by moving this electron up here, we now have 2 half-filled sublevels. And that is a little bit lower in energy. So you've got, in the hotel analogy, it's like there's a special, a Groupon maybe going on. There's a coupon. Where if you've got one person in each bed here, you get a discount that makes up for the difference in the cost of going into that other room. So it does this. Copper also does something strange. So what we expect for copper would be this. 4s2, 3d9. That's what we expect. But again, it's actually lower in energy to move that one up here, have all of these guys paired up, and this one half full. So my husband, we were talking about this last night because he has to lecture on this tomorrow. And he's got some insights that I've just never thought of. And so his analogy about this is, imagine holding 2 buckets of sand. Okay, they're heavy. And you start spinning, right? What happens? I'm only going around twice. The buckets, I'm dizzy. The buckets fly out, right? But you're balanced, and you can do that, right? What if you drop one of the buckets? And you're still spinning with the one bucket. Now you're out of whack, you're not balanced, and so it's called processing. You're rotating, but you're processing through space because you're out of kilter. Okay? So that's a bit of what's happening here. By moving this electron up here, this guy is balanced. Now we've got all these balanced guys and this one half-filled guy. So everything's symmetrical that way, if that helps you to remember. So copper and chromium are the 2 that I want you to remember the exception for. Yeah, she was just going to ask that. So you need to know those. I'm going to show you the rest of them, and if you encounter them, don't be shocked. Like, oh, it violates the rules. No, this is what they do, but I'm not going to require that you get these right on a test or anything. So molybdenum is similar to chromium, so it moves 1 electron from the S up to the D, and so each of these is half full. Ruthenium, I don't know. I don't know why ruthenium does this, but it's lower in energy, apparently. it'll move one up here, and so it's got this one half full, and that one's got 7 in it. That one just doesn't make sense to me. But it is what it is. And then palladium also does something strange. It'll actually move 2 electrons up from the S to completely fill its 4D. So I'm not going to require you to remember those because I have a hard time remembering them myself. But you do need to know chromium and copper. Okay? Any questions?